Okay, we're going to wrap up Chapter 9 with mostly some conceptual discussion here. So, in the previous video, we did an example with a piano wire that had a tension applied to it. And some of this may be common sense, or maybe you've heard these terms before, but just to make sure that we're all on the same page. A tensile force, putting something in tension, what we mean by that is that it's basically a pulling force. Tension is pulling. It pulls away at both ends of a linear object and it stretches it out. It elongates it. Okay, so this is tension. Contrast that with compression. So columns, for instance, that support a building are in compression. The forces are pushing in on both ends. We have the weight supported above, and then the normal force of the foundation pushing back, and the columns find themselves being compressed or shortened. So they still feel stress on their cross-section. Okay, but instead of pulling it apart and stretching it out longer, it's being pushed together and is being shortened. Okay, so this is compression. Now, shear stress. What shear stress means is shearing occurs when you have a plane, a shear plane, like the bottom of this rectangle, this rectangular cube, and the opposing forces, this force down here and this force up here, this force couple, rather than acting perpendicular to the plane as they did with tension and compression, they're acting parallel to this plane now. So when you have forces acting parallel to a particular plane, they cause shear stresses to occur. And what that does is rather than shortening it or lengthening it, it kind of makes it shift to the side. It makes it rack. It goes from being a rectangle to a parallelogram. So the amount of shear deformation is measured from, like in this case, the top right corner. How far does that top right corner shift over to the side? Or it'd be the same with this corner. How far does it shift over to here? Where the original length is measured in terms of the height perpendicular to the plane, delta L is how far over does it shift, and then the strain is still going to be equal to delta L over original L. Okay, and so this is shear. So those are the three basic types of stresses that can cause strain to occur in a material. Another thing that can happen, we've been talking about mostly linear type objects like that piano wire, that we apply a force to it, a tensile force, and it stretches out, it elongates. Okay, and one of the things that determines how much it elongates is its modulus of elasticity. But what if we're talking about a three-dimensional volume? Okay, if you had a balloon or a box filled with air or some other compressible gas, and we pressurized it and made it go in all directions, we could reduce its volume. So it wouldn't just be a matter of changing its shape in one direction. We're not just making it shorter or thinner. We're just going to make it smaller in 3 dimensions by compressing it. How can we calculate the amount of volume change we can expect based on a pressure difference? Well, here's a formula right here. So the change in volume compared to the original volume is equal to -1 over B times delta P, where delta P is the pressure difference, and B is a new term we're introducing called the bulk modulus. It can also be found in table 9.1. That's the same table where we found the modulus of elasticity. But bulk modulus applies to liquids and gases and things that don't have a distinct shape. So they don't have a modulus of elasticity. They instead have a bulk modulus. So like the person squeezing the stress ball here, you apply a pressure, an inward pressure on that ball, and it is going to reduce its volume. And like the formula here says, that change in volume compared to its original volume is equal to -1 over b times delta p. Okay, and so b is just something that you look up in the textbook. Delta p is the change in pressure, and delta v is the change in volume. V sub naught is the original volume. So eventually, if you apply enough stress to an object, it will break. So how do they break? Well, with tension, it ruptures. It fractures and ruptures and just breaks apart into two pieces. Compression members, they can be a little bit more tricky because many compression members are slender enough that they actually buckle or bow out to the side before they actually crush. But let's ignore that for now and say this is short and squat enough that it's not going to buckle. Then compression failure is just simply crushing. It just the material itself is crushed. And with shearing, again, the forces are running parallel to this plane, or actually this would be the shear plane right here, is where the material is actually shearing apart. And it's basically slicing into these two pieces, the bottom part going to the left and the top part going to the right, just like the two blades of a pair of scissors running parallel to each other. So that's a shear failure. Shear failure, it fractures along the plane and splits apart. Tension, and then just breaks into two pieces. And with compression, it crushes. Another potential failure mode for materials when a load is applied to them is bending failure. And this is essentially what I was talking about with a column. If you've got a tall, slender column, if I draw a little rectangular column here, its most likely failure mode is actually not going to be crushing, but buckling. It's going to bend out to the side. And if you think about it, the buckling of a column to the side is no different than the bending of a beam. A beam is laying down on its side already, typically is loaded in the vertical direction, and that causes bending to occur. Now, bending stresses are actually a combination of several other types of stresses. You have compression at the top. So imagine I've got a couple planes here connecting the top and bottom. These two planes would have been parallel when this thing was flat, but now that it's bent, the top two positions of the plane are getting closer together. And that forcing of the points to be close together is compression. At the bottom, they're being pulled apart. And when you pull things apart, that's in tension. So bending stress is really a combination of compression and tension. We see maximum compression stress at the top, maximum tension stress at the bottom, and if we connect the two with a line, kind of shade in this, kind of diagramming the stress values here, we actually have a point in the middle where there is no stress, no compression or tension, and this is called the neutral axis. So in a beam, the least amount of bending stress occurs right in the middle. There's an interesting case study. I'll post a video to go along with this. It was a hotel, I think, in Kansas City, Missouri, that had these elevated walkways, and the contractor decided to essentially take a shortcut and change the original design. And it was approved initially. Nobody saw the problem in it, but it quickly became apparent. Well, unfortunately, didn't become apparent until it was too late. But the change that was made from one continuous tensile support supporting both of these walkways to breaking it up into two separate ones effectively doubled the amount of stress in the top one, and therefore caused failure. So it's an interesting application of physics in the world of structural engineering, and it's important to not overlook some of these conceptual things, or sometimes some really bad things can happen. Yeah, this is just giving some further detail on it. When just one hanger was used for both decks and was continuous, the amount of stress caused by one was just equal to mg, the weight of that particular floor deck. But when we had two, you had this upper one had to support this and the one below, so it essentially doubled the amount of stress on it, which is what led to the failure. And then the last thing to talk about here, some ancient uses of compression stress. Masonry, rocks, rubble, bricks are excellent in compression, not very good in tension. So if that's the building material you're using, it would make sense to take advantage of that compression stress. A arch does so. All of these rocks are in compression, and the stress vector starts off horizontal and then changes to vertical. So you have all of these stresses, but they're all compressive, pushing down, down, down. So if you've got an arch that's supported in a wall, that's fine, that will help, because all these outward forces will be counteracted by the mass of all of these bricks to either side. And then the downward force is just accepted by the compressive stress of the rocks and whatever foundation it's sitting on. Okay, so an arch buried inside a wall, very strong, very good at carrying load. Now what happens is when you try to span a distance, well, here, let me go back to this. The cathedral here, Notre Dame Cathedral, it has these very tall, slender walls here. Okay, and so in order to prevent the arches in the roof from pushing them out, they have what are called these flying buttresses. These supports that are pushing back against the wall to keep it upright and to keep the forces from the arched roof from pushing the walls out. So one thing that can be done to improve the efficiency of an arch is to increase its height. So if we look at this shaded yellow part, it's essentially the weight that the arch is carrying. We can represent that with a single downward point load here. That is going to be reacted by the support at the end of the arch. But the thing is that we have to remember all three of our equilibrium equations, and the sum of the moments has to also equal 0. So if we sum the moments about this point, okay, we've got this force causing a moment or torque in that direction, this support pushing back up this way, and then we have the horizontal force. We have to resist the horizontal outward thrust of this arch, and it's going to push it back in this direction. But it depends on this moment arm, the height of the arch. And so if we can make the height taller, like in this instance, we're increasing the height from 4 to 8, we've made the moment arm larger. That allows us to make this force much less, because the torque is equal to the force times the distance. So if the distance is big, the force can be smaller. half as much, in fact.